Okay, Physics 20s, this is the lesson on energy. So for the most part, this should, except with the exception of one type of energy that we're going to talk about, it generally should just be a review of Science 10. I'm not expecting you to remember this, but it should, some of it should come back to you as we're moving through it. I'm not sure what the blip was. Okay, so we'll start with doing some highlighting of outcomes here. So in energy, our first outcome here is define mechanical energy as the sum of kinetic and potential energy. So that, again, is a review of Science 10. That's where we're leading to. What we're going to do is we're going to be looking at what exactly kinetic energy is and what exactly potential energy is. So in order to show me you've met this outcome, you need to define energy. You need to relate system international units to physics quantities. So that's being able to write energy in joules or kilogram. Oh, that is wrong. That should be kilogram meters squared per second squared. So that's missing a squared right there. You want to be able to define potential or gravitational potential energy, calculate gravitational potential energy, using EP equals mgh. Explain the necessity of identifying a reference point in the measurement of height for potential energy. Define kinetic energy. Calculate kinetic energy using EK equals 1/2 mv squared. Define elastic potential energy, and define mechanical energy as the sum of kinetic potential energy. And then just going back, elastic potential energy, you want to be able to calculate the potential energy stored in a spring using potential energy equals 1/2 kx squared, and then be able to solve for any variable. So that's solving for any variable. I'm going to highlight those bits for you as well. Okay. So that brings us to where we want to start making some notes here. Okay, so getting into just some definitions, and then we'll look at each of the three different types of energy, and then finally look at mechanical energy. Energy is the ability to change an object or its environment. When we talk about changing an object, we might mean things like we're changing the object's shape or the object's speed, things like that. Changing the object's environment, maybe we're changing the object's height, right, or its position. So starting to look through our different types of energy, we're going to start with potential energy. And as a general definition of energy, potential energy is just energy that's stored in an object due to its position or its state. So for example, there's really kind of, I guess, four main types of potential energy that we talk about in physics. Two that we deal with in Physics 20, one that we deal with in Physics 30, and then the other one that comes up that's more has to do with chemistry. But basically we have gravitational potential energy, which is one thing that we're interested in today. And that's energy that's based on it's based on height. Right? It's based on how high an object is over a reference height. So that's what gives an object potential energy, gravitational potential energy. Elastic potential energy is another one we're interested in. We talk about that briefly in this unit, and then it plays a big role in the next unit when we talk about oscillatory motion or periodic motion. So we talk about springs moving back and forth and things like that. So this is, it's based on what's called elastic constant. So it's based on how elastic an object is. And that, we'll talk a little bit more about that elastic constant when we talk about this type of energy. There is chemical potential energy. Chemical potential energy is the energy that we're harnessing when we combust coal for heat or for electricity. So chemical potential energy is based on the chemical bonds between elements and molecules in an atom. We'll just put based on the chemical bonds in an atom. Really what's going on there is it takes a certain amount of energy to hold the parts of an atom together, and for some substances, when you do something like that, like combusting coal, that releases that energy and turns it into another form. And then, very similar to chemical potential energy, is nuclear potential energy. So that's the energy that we're harnessing when we fission uranium. And that type of potential energy is based on the relationship between protons and neutrons in the nucleus. So based on protons and neutrons in the nucleus. Okay, so we will start by defining a little more specifically gravitational potential energy. Remember, you guys, you can stop and start and rewind this video as much as you need to be able to get all the material down. So gravitational potential energy, it's stored energy as a result of an object's height. Okay, and that height is above some reference height. Usually that reference height is the ground. But we can manipulate it to be anything. Okay? When we start talking about conservation of energy, that's when you start manipulating that reference height. Okay. So that was just my next little bit of notes here, is that you can manipulate the reference height. So what that basically means is you can make h equals 0 anywhere. And you just choose whatever is the most convenient spot to make that reference height 0. So the formula for gravitational potential energy, if you remember from last year, is EP equals m times g times h, where EP is the potential energy in joules, m is the mass in kilograms, g is the acceleration due to gravity in meters per second squared, so it's 9.81 all the time, and h is the height in meters. And that formula is on your formula sheet. So you don't have to memorize that one at all. The units, we'll do a quick little unit analysis with this just to come up with the units for potential energy. So if we start with the formula, EP equals mgh. Doing the unit analysis, remember, we're just basically writing out units for what we have here. So EP is in joules, right? Energy is in joules, and we can figure out what fundamental units joules are in by writing out the units for the rest of the formula. So mass is in kilograms, G is in meters per second squared, and H is in meters. So that means a joule is equal to a kilogram times a meter squared per second squared. Potential energy is a scalar quantity, and it depends on the vertical reference height. So it doesn't depend on any kind of distance traveled. So it doesn't really, no horizontal or other types of height are involved. So it depends only on the vertical height. So I can kind of illustrate this with a little bit of a picture. Just if we have a little guy on a slide. Okay, so we'll say this is our slide. Whoops, that's supposed to be a straight line. And this is our slide going down here. And let's say this is 4.0 meters, the length of the slide. And we've got our little guy up to the ground. So this is the ground along here. Right, so that would be our h equals 0. So that's our reference height. And our little guy sitting on top of the slide. Okay, like that. And that's the height of the slide. So the potential energy only depends on, when he moves down the slide, right, like he moves down the 4 meters, but his change in height is that difference there. That's the change in height, so that's where the potential energy is referenced from. And if we know that this angle in here is 30 degrees, then we can use simple trigonometry to figure out what that h is, right? Because sine of 30 degrees equals h over 4 meters. So h is equal to 4 meters times sine of 30 degrees, which in this case gives you 2.0 meters. So what I'm trying to illustrate here is that the change in potential energy has nothing to do with his movement down the 4 meters. So this movement going down here from the top of the hill all the way down to the bottom, that doesn't matter. The 4 meters that you traveled doesn't matter in terms of potential energy. What only matters is his change in height. So EP depends only on the height he started from. Not on the 4 meter distance down the slide. Okay, so we'll just move into some formulas, or some examples using the formula. Okay, so we have a 900 kilogram elephant is walking up and down a hill as shown in the diagram. At its highest point, so that's at point C here, the height is 32.5 meters above the ground. So then we'll make A is the ground. And with there's a flat portion here at point B that has a height of 18 meters above the ground. And we just want to find the elephant's potential energy at each of those 3 points. So at point A, so at each of these, I'm just going to repeat this, where the height is equal to 0 at A, height is equal to 18 meters at B, and the height is equal to 32.5 meters That's C. So for part A, potential energy is M times G times H, which in this case is 900 kilograms times 9.81 meters per second squared times 0 meters. So that means there's no potential energy at point A. So 0 joules of energy. At point B, again, EP equals mgh. So we've got 900 kilograms times 9.81 meters per second squared times 18 meters. So that means his potential energy is 158,922 joules, or with proper sig digs, 1.59 times 10 to the 5 joules. You start to see that energy is actually, like the unit for energy, joule, is pretty small, so the numbers we get for energy is actually a pretty big number. And then at point C, just going to put in little subscripts here because that will help when we get to later types of calculations when we're talking about conservation of energy. So point C, we've got 900 kilograms times 9.81 meters per second squared, just squish a bit, times 32.5 meters. Okay. So again, we should get a much larger number, almost twice as big as we did for point B. So we get 286,942 joules, or 2.87 times 10 to the 5 joules. Okay, so we'll work with, so that's pretty simple. You just pick a height. Now, so we could have also called this a reference height here. If we called B a reference height, then at point C, we just change what height we're using. We find the difference between these two numbers, and that would change how much potential energy it has here, which isn't really changing the situation. Like, you're just changing what you're calling your reference height. So sometimes it can make calculations easier when we're doing conservation of energy. So we want to determine how high above the ground the elephant is. Remember, we have a mass of 900 kilograms, and our G is 9.81 meters per second squared. And we have a potential energy here of 5.34 times 10 to the 6 joules, which is much larger than anything we have here. So we're going to get a height much larger than the actual cliff, right? Okay, so EP equals mgh. So H equals EP divided by mg. So 5.34 times 10 to the 6 joules divided by, and big bracket here, 900 kilograms times 9.81 meters per second squared. Big bracket. So you want to multiply those two together before dividing by them. And you get a height of 605 meters. So we're way off the cliff there. We're hanging in midair. Okay, and determine the change in gravitational potential energy as he moves from point B to point C. So change in potential energy, remember that change means final, so EP final minus EP initial. Okay, so final, that's going to be at point C, right? Because we're going from B to C. So the final is point C, and the initial is point B. So if I could just sneak up here a little bit, so 286,942 joules minus 158,922 joules. And that equals 128,002 joules, like that, or 1.28 times 10 to the 5 joules. You could have also, right, if you didn't actually have this calculated out, then what you're doing here is you would just do mg times h the height at C minus mg times the height at B, or mg times the difference in those heights. And when we start talking about work, we'll we'll be doing calculations that fit that. Okay, so we'll look at elastic potential energy next. And it's another type of potential energy. Elastic potential energy is energy stored in an elastic object. When it's deformed. So a couple of things here. An elastic object, it's things like, obvious things like an elastic or a spring or a trampoline. Trampoline, not sure there. A bow, like a bow and arrow. Concrete is also a springy object. And deformed basically means stretched or compressed. When the object returns to its original shape, it no longer has any elastic potential energy. The formula, okay, so it's also potential energy, so it's EP, and it equals 1/2 times K times X squared. Okay. So I've got EP, that's what's on your formula sheet. Sometimes I write this out as EPE just to keep it straight from gravitational potential energy, but it doesn't really matter. Okay. And so then energy again is in joules. The spring constant, which is K, is this thing measured in newtons per meter, and X is the deformation, how much you've stretched it or compressed. So this is stretch or compress, and that's measured in meters. Okay. Now that spring constant, just a little note about that. Okay, that is a measure of how easy it is to stretch or compress, to deform an object. So a measure of how easy it is to stretch or to deform an object. And it's unique to each object. And it's a measure of how many newtons of force are needed to deform an object by 1 meter. And that's sort of what it means there. This elastic potential energy formula is on your formula sheet. Okay. And again, we can look at the units to show that we get the same units for energy as we did with gravitational potential energy. So we start with the formula. We know that potential energy is in joules. Okay. The 1/2 doesn't matter because it's a constant. It doesn't have a formula, so we just ignore it. K is a Newton meter, and X is a meter, and then that's squared. So then what we know over here from F equals ma is that a Newton equals a kilogram times a meter per second squared. So we're going to replace that newton. So we have kilogram times meter per second squared divided by meter times meter squared. So what that gives us is a joule is equal to, if we look at our units here, we can cancel this meter and cancel this meter, and so then this one is multiplied over there. So we get a kilogram times a meter squared per second squared. Then just a little note on equilibrium position. So equilibrium position is this thing when the object returns to its original state. So that's the equilibrium position, is what that is. That original state is called the equilibrium position. Okay. And it's the rest position of an elastic object. And that would be where the potential energy equals 0. So as an example, we can look at a spring. Okay, we have a spring. Okay, so the spring, like, we can just say like when it's just kind of sitting normally, that's a really badly drawn spring, but that would be the equilibrium position. And at that equilibrium, potential energy equals 0. Then with the spring, we can have two things happen. We can stretch it out to some extra length. Okay, so we're stretched. But the other thing I want to point out here is that that value there, that difference in the stretching, that's x. So then this is stretched. And so EP equals 1/2 kx squared, where the x is how much you've stretched it. You can also go the other way. You can compress it. So it gets really close together. So there it's compressed like that. And again, how much you've compressed it, that difference between the equilibrium position and where it's compressed to, that's x. And again, EP then is based on that x, so 1/2 kx squared. Okay. And then another formula that we need to be aware of is this thing called Hooke's law, which is just a force formula. Okay, so it says that the restoring force, Fs, is equal to K times X, so the spring constant times the displacement with the equilibrium position, or how much it's stretched or compressed. On your formula sheet, that contains a negative number, or a negative in front of it. Don't worry about the negative for now. You can just ignore it. We'll talk about what that negative means in the next unit. That becomes kind of important. Then this is also on your formula sheet. Okay, so now we'll just do a couple examples using those formulas. Okay, how much energy is stored in a spring that is stretched 18 centimeters if the spring constant is 118 newton meters? So X is 18 centimeters, which is 0.180 meters. K is 118 newton meters, and we want to know potential energy. So it's a pretty straightforward formula. EP equals 1/2 kx squared. So 1/2 is 118 newton meters times 0.180 meters squared. Okay. And that will give you 1.91 joules. When we're talking about elastic potential energy, it tends to be a pretty small number. Okay, a force of 33.8 newtons. So that would be our restoring force. 33.8 newtons causes the spring to stretch to a length of 25 centimeters, so 0.25 meters, beyond its equilibrium position. So for part A, we want to determine the spring constant. So we know that we're going to use Hooke's law. Fs equals k times x. So k is equal to Fs over x, which is 33.8 newtons, divided by 0.25 meters. And we get a spring constant then of 135.2 Newton meters, which with sig digs is 1.4 times 10 to the 2 Newton meters. The bigger that spring constant is, the harder it is to squish or stretch that spring. And then we know what is the elastic, we want to know what is the elastic potential energy stored in the spring. Now that we've found our spring constant, we use EP equals 1/2 kx squared. So EP is 1/2 times 135.2 Newton meters. So I'm using the unrounded number there. And then that's times 0.25 meters squared. And that equals 4.2 joules. Okay, our next kind of energy we're going to talk about is kinetic energy. Okay, and kinetic energy is the energy of an object due to its motion. The energy of an object in motion. So if an object has velocity, it has EK. So the formula, kinetic energy is equal to 1/2 mv squared. That's on your formula sheet. And the most common rearranging of this is solving for velocity. So let me just write that down for you in brackets over here. If we rearrange that to solve for velocity, we get 2 times EK divided by m, and the square root of that gives us velocity. Unit analysis. So EK equals 1/2 mv squared. EK is in joules. The 1/2 we ignore because it doesn't have a unit. Mass is in kilograms. And velocity is meters per second, which is meters per second, and then that's squared. So that shows us that a joule is equal to a kilogram times a meter squared per second squared. And again, kinetic energy, all types of energy, they're scalar quantities. And this should be obvious. There's more kinetic energy in an object with more mass and or a bigger velocity. So again, pretty simple formula for using. We have a 60 kilogram student is running at a uniform speed of 2.70 meters per second. We want to find what the student's kinetic energy is. So EK equals 1/2 mv squared, which is 1/2 times 60 kilograms times 2.70 meters per second squared. Okay. And again, kinetic energy, well, it's not as big as potential energy, but it depends on the velocity and the mass. In this case, we get 218.7, or with sig digs, 219 joules of potential energy. We can also rearrange it to solve for other things. So we want to determine the velocity of a 150 kilogram cart. So this is going to probably have more kinetic energy because it has more than twice the mass of our student. And it has a kinetic energy of 3.60 times 10 to the 4 joules, which means that cart's moving pretty fast. So EK equals 1/2 mv squared. We want to multiply both sides by 2 to get rid of the 1/2. So 2 times EK equals mv squared. Then divide by m. And take the square root, and that'll give you velocity. That is probably the most commonly rearranged formula used in physics in high school, is solving for velocity with the kinetic energy formula. So 2 times 3.60 times 10 to the 4 divided by 150 kilograms. And then a very common mistake is to forget to square root, so don't forget to do that. 21.9 meters per second is a much more reasonable answer for velocity than, say, is 400 meters per second. Okay. A couple different types of questions. So an object is traveling in a straight line at a constant velocity with a kinetic energy of 4.0 joules. We want to know, we're going to triple the speed, so V becomes 3 times V. So what's the new kinetic energy? So one of those proportionality questions. Okay, so kinetic energy is directly related to the square of velocity. So if you square the velocity, we want our new EK, that means that new EK has to be directly proportional to whatever factor we're multiplying velocity by squared. So that EK new is directly proportional to 9 times V squared. So to find our new EK, we're going to take our old EK and times it by 9. So that gives us 36 joules as our new EK. Okay, Andrew is driving his 1,200 kilogram Triumph TR6 down the street at 52 kilometers per hour. So that's his initial speed, 52 kilometers per hour, which we'll divide by 3.6 to get into meters per second. So that is going to give us 14.4 meters per second. He notices that there's a school zone ahead, so he hits the brakes to slow down to a final velocity of 24 kilometers per hour. Divide that by 3.6, and that gives us 6.67 meters per second. We want to know his change. If he slowed down over a distance of 145 meters, the distance doesn't actually matter. We want to determine the change in kinetic energy. So let's remember, change in kinetic energy is final minus initial. So EKF minus EKI. So that's 1/2 mVF squared minus 1/2 mVI squared. That V is supposed to have a little vector hat, but I find it actually kind of hard to get the vector hat on with the squared, so I leave it off. So it's not a big deal to not include it on there. So 1/2 times 1,200 kilograms times final velocity, which is 6.67 meters per second, and then that's squared, minus 1/2 times 1,200 kilograms times 14.4 meters per second squared. Okay, and that equals 26,667 joules minus 125,185 joules. And so that gives you negative 9.8 times 10 to the 4 joules. So it is going to be negative, right, because you're losing kinetic energy because you're slowing down. You could also, if you're a little bit more comfortable with algebra, and I won't carry all this through, I'm just going to set it up for you, but you can set up that change in EK being EK final minus EK initial. That can be 1/2 m times VF squared minus VI squared. But be careful, because VF squared minus VI squared is not the same as VF minus VI squared. You can't do that. You have to square them first and then find the difference. Okay, so last concept here is mechanical energy, and we're putting everything together here. So we're putting a few things together. So potential energy, or mechanical energy, is the sum of kinetic plus potential energy. So the sum of the potential energy, the potential and kinetic energy of an object at a given time. So it's pretty easy. It is, and this we should remember from Science 10 as well, mechanical energy equals potential energy plus kinetic energy. So mgh plus 1/2 mv squared. It's rare, but you could also have 1/2 kx squared plus 1/2 mv squared. But when we're talking about mechanical energy, we tend to be using it this way. This is not on your formula sheet. Okay, so this is not on your formula sheet. You need to memorize this. Okay. So find the mechanical energies. We want EM of an 800 kilogram roller coaster. It's traveling at 15 meters per second and is at a height of 12 meters. Okay, so mechanical energy equals potential energy plus kinetic energy, which is mgh plus 1/2 mv squared. So 800 kilograms, thinking about the elephant, times 9.81 meters per second squared, times 12 meters, plus 1/2 times 800 kilograms times 15 meters per second, and that's squared. And be careful, because a lot of students will write this down and even write down the squared here, but then they'll forget to square that velocity when they're actually calculating it. So the potential energy is 94,176 joules, and the kinetic energy is 90,000 joules. So I'm just writing that in there so that if you didn't get the same answer as me, you can go back and see maybe where things went wrong. So we get an answer of 1.84 times 10 to the 6, or sorry, 10 to the 5 joules. So that's pretty easy. A slightly more challenging question is having to find either the height or the speed when you're given other things. So we want to know how high above the ground is a 1.16 times 10 to the 5 kilogram airplane that's flying at an airspeed of 720 kilometers per hour. So we'll divide that by 3.6, which gives us 200 meters per second. And we know that the mechanical energy is 8.49 times 10 to the 9 joules. So mechanical energy is the sum of potential energy plus kinetic energy. To find the height, we need to find EP. Right? So we're going to find EP. So we'll rearrange this for EP. So EP is mechanical energy minus kinetic energy, which is 1/2 mv squared. So that is going to be 8.49 times 10 to the 9 joules minus 1/2 times 1.16 times 10 to the 5 kilograms times 200 meters per second, and that's squared. Okay. So that's going to give you this big number, 617, and then I believe it's 7 zeros. So let's see, thousand, million, billion, so 6,170,000. So then that means EP equals that, and EP is mgh. So H is equal to EP divided by m times g, which is 6,170,000,000,000, I don't know, 6,170,000,000. There we go. Now I got it. Divided by 1.16 times 10 to the 5 joules times 9.81 meters per second squared. And remember, just make sure you multiply those two numbers together before dividing. So then you get a height of 5,421.98 meters So we can write that as 5.42 kilometers. Okay, so that is the energy lesson. So just to go ahead a little bit here, I'll tell you what questions you can work on for practice if you feel the need to practice some of this stuff. And remember, you can go back in this, you can rewind, you can watch this as many times as you need to get the material down. For practice questions, page 178 to 181, numbers 1 to 9 and 11 to 13. Page 183 to 185, numbers 1 to 7. And page 193, number 5. And then in your text, page 309, numbers 1 to 3. I think like these two are elastic potential energy. And then these two are kinetic and potential. I can't remember exactly which one is which. And then there's some reading at the back of your notes booklet, page 28 to 31. Good. Have a good day, guys.